as you and you generate natural numbers by generating collections of things that instantiate these natural numbers. But it's impossible for there simultaneously to be infinitely many natural numbers. So the natural numbers, according to Aristotle, are potentially, but not actually, infinite. And more generally, potentialism, which is my topic, is the view then that certain types of entities, like the natural numbers for Aristotle, are successively generated and generated in such a way that it's impossible to complete this process, as it were, of generation. So that's the topic. And more specifically, I'll be concerned with the question of what is the correct logic for reasoning about all entities of some such type. So a domain of entities that are potentially infinite, and just that, so not an actual infinity. And it's been known for some time then that under certain plausible assumptions, you may use classical first-order logic for that kind of reasoning. So I'll explain this in detail as we go along. Yeah. And it's also been known that the traditional logic of plurals, by contrast, has got to be restricted. So very interesting difference here between first-order logic and higher-order logic, specifically the logic of plurals, where the former can proceed in a classical ordinary way, while the latter needs to be restricted. And my aims today are to actually identify the correct plural logic for that kind of reasoning. So we've known that you can't have the traditional logic of plurals, but we haven't known what the correct logic of plurals is. And this also has a somewhat more surprising side benefit, namely paving the way for an alternative analysis of potentialism, as I presented it on the previous slide. So I'll give you one example of how that alternative analysis can be used. So here's the plan for today. So I'll review the modal analysis of potentialism. So using modal operators to analyze that view that I started with, and explain to you why classical first-order logic remains valid for reasoning about merely potential domains. Then the bulk of it will be about the logic of plurals. So I will give an account of how you should combine modal resources with plural resources, and then provide or outline a faithful interpretation of a certain very basic logic of plurals in a modal logic of plurals, and strengthen that to a result about definitional equivalence, and then end with some examples, or one example is I think all I have time for, of how that framework can be used to analyze potentialism in a way that uses no modal operators. So it's a great simplification of what has been known so far. But let's start with modality. At least for those of you with a background in philosophy, this is quite a natural way to proceed. So take Aristotelian style potentialism about arithmetic. So the view then is that necessarily, however many natural numbers you've got, it's possible to generate yet more. So necessarily, for any number, it's possible for there to be a successor. And this contrasts with the notion of an actual infinity, which says that for every natural number, in fact, there is a successor. So according to Aristotle, 2 is not possible. Okay, so that's the combination of Aristotelian views that yes, the natural numbers are potentially infinite, and no, they are not actually infinite. And that view dominated for a long, long time in the philosophical tradition, and was really just superseded once Cantor came around and convinced the majority of mathematicians and philosophers that transfinite set theory was a good way to go. However, even in Cantor, you'll find remnants of a kind of potentialist view namely when you talk about not the natural numbers, but the whole hierarchy of sets. So I have in mind here these famous passages from Letters of Contours where he talks about inconsistent multiplicities. And one way to go with those Cantorian ideas is, again, as a kind of potentialism. So necessarily for any object, here I use plural resources, for any one or more objects, XX, possibly there is their set. Right? So it's always possible to use some given objects to define their set. So necessarily it's possible that there is the associated set. And this contrasts again with the corresponding actual or completed infinity, which would be that for any object, in fact, there is the associated set, which in the naive setting takes you straight to paradox. So, of course, Cantor would deny even the possibility of that in a way that mirrors really how Aristotle denied the possibility of two on the previous slide, an actual infinity, in his case, of natural numbers. And here's the connection with Gödel, which I find interesting. So I'm sure you all know this famous passage by Gödel where he lays out, in my view, for the first time ever in a clear way, the iterative conception of sets. So the concept of set, he writes, according to which a set is anything obtainable from the integers or some other well-defined objects. Note the plural here, object, by iterated application of the operation set of, has never led to any antinomy whatsoever. That is, the perfectly naive and uncritical working with this concept of set has so far proved completely self-consistent. Okay, so you have this set of operation, and that can be applied to any well-defined object. And here's the connection then I'm interested in with the previous material. So what do we mean by some well-defined objects? So it's pretty natural to think that every plurality of objects is or makes up some well-defined objects. Right? So whenever you have some things, you could apply the set of operation to define the associated set. And if so, you're in a situation very much like that on the previous slide, that set you could define as potential relative to the plurality of things you had got, but had better not be actual, had better not be already there. So there is a nice connection with Gödel too here, at least on one plausible way of reading that passage. I'm not saying that's the only possible way of reading it, but it's one way of taking it. And here we can now zero in on my main question. So what is the correct logic for potentialism, for reasoning about a domain of objects that are potentially infinite, but not actually infinite? And then, of course, ordinary mathematics is done in a completely non-modal language. So call that language L. And the analysis I have outlined of potentialism is given in a corresponding modal language, where we add to L modal operators to obtain what I call L diamond. And the question I'm interested in of the correct logic for reasoning about potential infinities is a question that arises in the non-modal language. Right? We want to know what logic can ordinary mathematicians or logicians not using modal resources use when reasoning about these kinds of domains. Okay, so we have that question as it arises in the non-modal language. Excuse me, and the answer then will depend on two factors. First, you've got to connect the non-modal language with a modal language. You've got to define a translation from the former to the latter. And then secondly, we need some sort of modal theory, call it T diamond, in the modal language L diamond. Okay, so once you have fixed these two factors, the translation from one language to the other and the theory in the modal language, you can answer the question of what is the correct logic back in L. Okay, so I pause there for everyone to get a chance to absorb that, since this will really frame the entire remainder of the talk. So the first factor then of translating from the non-modal language into the modal language. The translation I favor and find very natural for these purposes is something I call the potentialist translation. And the idea is that you can use necessarily for all and possibly the rest to generalize across all stages of some process of generation. Right? So across all stages of one of these potentially infinite domains. And when you have a formula phi of the non-modal language, you translate that by simply replacing every universal quantifier with necessarily for all, existential with possibly there is, and call the result of translating in that way phi superdiamond. Okay. And the claim then is that this translation provides the desired translation for our purposes. And why is that? Well, existence talk in the non-modal language is now given a potential analysis, right? So existence is potential existence, right? So that makes good sense when you're analyzing potentialism now. Then to get the result I'm after, that you can use classical first order logic for this purpose, you need some background assumptions. So one background assumption is that you have so-called stability of atomic predicates. So if an atomic predicate holds of some objects, it keeps holding as you generate more objects. So once a member of a set, say, always a member of that set. Sets don't lose members or don't gain members from among objects you already had around. So you also have this negative stability. The modal logic, given that it's natural to take accessibility here to be reflexive and transitive, modal logic should be at least as 4. More interestingly, there's an assumption about what you do in cases where you have a choice of what to generate. So you've got a bunch of objects. You could generate more objects so as to get here or so as to get there. And then this convergence assumption says that it doesn't matter what you do. You could always bring the two ontologies back together again. So the ability to generate never goes away. You could always later on exercise that ability. And this licenses one more axiom known as G, and the result of adding that to the modal logic is S4.2. And here we get the validity of using ordinary classical first order logic for these purposes. So suppose on the modal side, you plug in everything I've mentioned so far. So S4.2, the stability axioms, that's over on the modal side. Then you may use just ordinary classical first order logic on the non-modal side. So one is mirrored in the other, so to speak. So I call this a mirroring theorem. It's also a result about faithful interpretability. Okay. So the upshot is that if you accept what I put in on the modal side here, then you're entitled to classical first order logic in the non-modal language, even though you're reasoning about a domain that is merely potentially infinite. Now here's the question as it gets analyzed of correct plural logic. So the most interesting aspect of plural logic for our purposes is the question of plural comprehension. So which pluralities are there? For which formulas phi can you talk about all and only the phi's, some things that are all and only the phi's? And then you analyze this in the way we have seen now. So you take that question as it arises in the non-modal setting, translate it by the potentialist translation into the modal setting. you get this questions for which formless phi or phi diamond is it possible for there to be some things that necessarily are all and only the phis. And we want to know which plural comprehension axioms are validated in that way. Okay, so we have the translation already that I've told you about, but we need a modal logical plurals to plug in here. And once we have identified that modal logical plurals, it's just a technical result to identify then the correct plural logic for reasoning about merely potential domains. And that way we could also plug that logic into this nice Gödelian idea that you have this set-off operation that can be applied to any well-defined objects. So next task is to say something about the correct modal logic of plurals. So here is just a super quick reminder of the modal logic we are using. So it's S4, we add the G axiom, and you have the rule of necessitation in the ordinary way. Okay, so no surprises there. For those of you who have seen plural logic before, there are also no surprises on this slide. So here is plural logic without modality added yet. So very often you have an axiom to the effect that pluralities are non-empty. To talk about some things, there's got to be at least one thing among those things. We may consider dropping that, since if you use pluralities to obtain sets, if you want an empty set, you also need an empty plurality. So I sometimes allow myself that. Then you have these plural comprehension axioms, which I already talked about. So for which formless phi can you have all and only the phis? And then plural indiscernibility. So when two pluralities are coextensive, then whatever holds of the former holds of the latter. Okay, with the usual restrictions we're familiar with from Leibniz law. It's a kind of Leibniz law-like principle. The most interesting material from this modal logical plurals, far and away, concerns the interaction of the two. This gets a little bit fiddly, but there is one very simple idea that I want you to take away from this. And that is that a plurality, as I'm talking about it, really just is shorthand for talking about some things. So a plurality really is nothing over and above some things. So when you track a plurality from one possible world to another, you've got to do so in terms of its members. That's all the material you've got to go on. So you track pluralities in a rigid or extensional way in terms of members. So then you get very naturally stability of plural membership. You also do a trick based on a version of the Barkin formula for restricted quantification to ensure that pluralities can't gain members even when the domain expands. And you can then get corresponding principles for the among relation. So to be among some things, that too is stable, right? So if some things are among some others, then they will always remain so, even when the domain expands. And you have a version of the Barkin formula there too. The resulting modal logical plurals based on that simple key idea that I mentioned, I call MPFO plus. PFO plus is ordinary plural logic, and here we just add modality in the way described. And now we can actually observe in a precise way that traditional plural logic has got to be restricted. Since traditional plural logic says there's a universal plurality, right? A plurality of which everything is a member, that translates into possibly there are some things which are necessarily everything. But that, of course, flies straight in the face of potentialism, which says that necessarily, however many things you have, there could be yet more. Right? Potentialism says that you can always generate more. So if one is attracted to potentialism, you can't have the traditional plural logic in the non-modal language L. So what we've got to do is to identify the correct plural logic to have in the non-modal language L. And we're going to do this in the way I've told you about already. So here's just a very quick reminder. Question arises in the non-modal language. The answer will depend on the translation, the potentialist translation I've told you about. And now we plug in the modal logical plurals I also told you about. So now we have the resources to answer this question. And before I give the answer, I've got to introduce a system of plural logic, which is required to state the answer. So first, we have a very weak system I call adjunctive plural logic, which says that there are singleton pluralities. So given anything, you can circumscribe the corresponding plurality of those things. Given two pluralities, you can circumscribe the plurality of those two, kind of union plurality. And then lastly, a plural separation principle. So if you have circumscribed a plurality of a bunch of things, and you got a notion phi, you could use that to select out or separate out the phi's from among the things you have circumscribed. And they are circumscribed in turn. And then, unsurprisingly, given that I spent time on introducing this basic plural logic, that turns out to be the logic that is validated in the non-modal language when you proceed in the way I have told you about. Okay, so we plug in the modal logical plurals I told you about. That all gets plugged in on the modal side. We translate in the way we've seen. And then basic plural logic is the logic that gets validated in the non-modal language. Okay, so we now have an answer to the question, at least an answer conditional on us accepting this modal logical plurals that we plug in. Of course, if you plugged in a somewhat stronger or somewhat weaker modal logical plurals, that may have consequences and indeed will have consequences for the logic you validate back in the non-modal language. And in fact, you can take this even further and define a kind of reverse translation. And so we have the first translation, the potentialist translation. It would be nice to be able to translate in the reverse direction. That's far less obvious since the modal language has extra expressive resources not present in the non-modal language, or so it would seem. However, it turns out to be possible to simulate quantification over possible worlds, even in the non-modal language. And this works because a possible world can be represented simply by a plurality of objects, namely the many objects that make up the domain of that world. And this works when we think about it, because all atomic predicates are stable. They don't change as you go from one world to another. And also because accessibility between the worlds is convergent. So when you have two different worlds, they can't disagree, since they can be brought together again later on, which means that they can't disagree on any of the literals. So a plurality of objects from the domain suffices then to represent a whole possible world. And this slide just spells out the more intuitive conceptual idea you had on the previous slide in a precise way. So to keep an eye on the time, I will go over this rather quickly. You have a translation now from the modal language to the non-modal one based on the idea I mentioned. And it's a kind of relativization idea. So square bracket sub VV, that is phi seen, as it were, from the point of view of the possible world represented by VV. So what is it for everything to be psi in that sense? Well, everything available among VV to be psi, or the translation of psi. Likewise for plural quantification. And then what is it for phi to be necessary from the point of view of VV? Well, for any extended plurality that also represents a world, so you may want to add the stuff I have in red ink here. That's optional, but it's often nice to add. So if that extended plurality also represents a world, which I capture by the antecedent here, then phi holds of that too. Okay, so that's the idea. And we're calling this the relativization translation. And then we get our final technical result towards answering this question of the correct plural logic for merely potential domains. And this takes the form of a definitional equivalence result. So we have the two systems I've talked about, or to be strict, some very slight modifications of them. You add just a tiny bit to get this result to come out in such a way that both of the translations I've talked about give you an interpretation, and indeed a faithful interpretation of one system in the other, and also such that the round-trip translations go first like that and then back again. That is logically equivalent to just staying put in L, and likewise on that side, right? So definitional equivalence. So you have a very strict proof-theoretic equivalence between these two systems: the basic plural logic and the modal plural logic that you use to give your modal analysis of potentialism. So that's kind of exciting, since in the literature, people have been using modal resources to analyze potentialist ideas. So using this as a framework in which to analyze potentialism. But then in light of this definitional equivalence, you could also use the non-modal system of basic plural logic to analyze potentialist ideas. And the equivalence between these systems is so tight in the form of this definitional equivalence that it should be possible, and indeed is possible, to give analysis of potentialism in a non-modal setting much easier. Since modal resources, I like them, but they are unfamiliar to many of us. And this raises a nice question of, given that you can eliminate modality from one of the frameworks in which you analyze here, what happens to the disagreement between potentialists and actualists, who say that, oh, this domain is merely potential, and no, it is an actual domain? Has that disagreement somehow been undermined by this result? Is a good question to ask here. So my plan then for the last, maybe I'll take 5 more minutes and go ever so slightly over time, if that's all right, is to connect up with a nice Gödel quote on the iterative conception and to try to answer that question. So basic plural logic, we can use that now to analyze a version of set-theoretic potentialism. And we remember that that was based on the idea that there was some evidence for already in Gödel that whenever you have some objects, you could use those to define their set. If that is what you do, it's very natural to have these correspondence principles linking pluralities and sets. So for instance, given two pluralities, their sets will be identical, just in case the two pluralities are coextensive. Similar claim for membership. So Y is a member of the set of XX, just in case it's one of XX. And since we take every set to be generated in that way, you may want to, or probably want to, add an induction principle that captures that idea. Then we can go ahead now and use those correspondence principles and basic plural logic to prove various set-theoretic principles. So you prove very easily extensionality, foundation, empty set, if you have an empty plurality, pairing, separation. And then remember the red ink stuff where I said that you've got to make sure that the pluralities you're quantifying over when you simulate worlds really do correspond to worlds. And to correspond to a world, a plurality presumably has to be transitive. right? Since if it contains a set, it's also got to contain the material from which that set was formed. And perhaps you also want to ensure that that plurality is supertransitive in this sense. So the idea here being that if you formed one set that is present at one world, you also have the resources to form every subset of that set. So those two are at that world. That means supertransitive. And then you can prove union and power set. So now you're really getting somewhere. And then you can get the remaining axioms from a slight extension of basic plural logic. This is something Salvatore Florio and I do in a forthcoming book, which I show the front page of here. Let me super briefly tell you about the extensions that I mentioned here. So far, we've had a very simple union principle that says that you can take the union of any two pluralities. But what if you have a plurality of tags that you put each as a tag on a plurality of things? Then the whole thing is a plurality. The whole thing can be circumscribed. So that's a kind of generalized union principle that gives you replacement. And it's very natural to follow Cantor and say that at least we have some pluralities that are actually infinite. So there's an actually infinite plurality of natural numbers, for instance. And that gives you infinity. And then you're up to all of ZFC. So that's neat. So the upshot then is that when you have a potentialist setting, so a kind of potentialist iterative set theory with plurals, you get a very nice route into ordinary first order ZFC. But what you get is first order set theory. The plural resources don't give you any extra logical or mathematical power, since the pluralities are all used to form sets. So you don't have proper class-sized pluralities, or so says the potentialist. By contrast, the actualist will say that no, the sets here form an actual domain, and for that reason you have pluralities corresponding to proper classes. So that'll give you second order set theory. So you see then that although we have in this way of analyzing set theoretic potentialism, although we have eliminated the modality, at least for practical purposes, substantive disagreement between potentialist and actualist remain. So potentialists say that you only get first order set theory. Actualists disagree and say that when you add plurals to set theory, you get second order set theory. So that's a very real substantive disagreement. So the disagreement here has in no way collapsed or evaporated. And finally, then connecting up with Gödel again. Remember Gödel's intriguing talk about the set-off operation that you can apply to any well-defined objects so as to form their set. Now we have a good way of making sense of Gödel here, at least one way of taking him that I find very illuminating. And you can see that as a kind of factorization of the iterative conception of sets. So you now separate two things. You separate what Bernays famously called quasi-combinatorial reasoning, right? So taking combinatorial principles that are valid in finite domains and applying them now to infinite domains. That you get by means of one of these plural logics that I have talked about. Maybe the stronger one with the generalized union principle and the infinity principle. So that separates out in one factor quasi-combinatorial reasoning, but no new objects, just that powerful kind of reasoning. And then the new objects come from the second factor, which in Gödel's case is the set-off operation. Right? So you have a single principle that generates the new objects, the sets, and then you have another package of principles that gives you the quasi-combinatorial power. And of course, this invites generalizations, since you can now take the second factor and either replace Gödel's set-off operation or supplement it with other principles. Right? So you could generate numbers of various sorts, cardinal numbers. You could tweak this a bit, generate ordinal numbers or generalized numbers, as Cantor did in the famous Grundlagen. So you can generalize a lot here. And since I'm over time, I will end there and make sure we have at least a little bit of time for discussion. So thank you very much.